grade, so looking at problem 22 from section 3.6, and we're asked to determine whether or not the subsets here of continuous functions on R is or is not, or are not linearly independent. So for this problem, we have set 1 sine squared of t and cosine squared of t. So a couple things to keep in mind. With our test with the Wronskian, that's often sort of people's first thought. That's only good for showing they're linearly independent, right? So if we tried to do that, you might run into a little bit of a mess, and you would end up not being able to conclude that they're linearly independent, because you're going to find that your Wronskian of 1 sine squared t cosine squared of t will in fact be 0 always. And so because of that, we won't be able to conclude to anything, right? If there's an opportunity to find it's non-zero, that's when you can conclude it's linearly independent. But the lack of that is just inconclusive. So what we would need to do is go one way or the other. Find a different method to prove it's linearly independent or linearly dependent. Now, the burden of proof is often on proving it's linearly independent, and all it takes to prove it's not is a counterexample. And so it's actually easier to prove things aren't. So let's just find a counterexample. So looking at this, we can say, well, I could write that first function 1 as a linear combination of the other two, because 1 is equal to sine squared t plus cosine squared t, which tells me that I could, if we were talking about a more sort of vectory notation, right? So with our Wronskian, you can say, well, if I had some constant f1 plus some constant f2 plus some constant f3, I can show these are 0 for some non-trivial c1, c2, c3. In this case, I can say if f1 is 1, etc., I could rewrite this thing as saying if c1 is -1, c2 is 1, and c3 is 1, I will in fact get 0. All right, that's a sort of a fancy way of writing out this equation here. So because of that, this example is linearly dependent. Notice the conceptual part of it is that I could write one of these as a linear combination of the others. So this 1 is sort of a useless addition. And so this right here is really the conceptual part, sort of the down-to-earth intuition. But if you want to go back to the definitions, right? So the definition of linear independence of vector functions, we define those by saying they're linearly independent when the only solution to this is all the c's being 0. And if there's any time where you can solve this without the c's being 0, they're linearly dependent. And here is the time, right? In fact, for any t with these c's, it works. And so this is going back to the definition here, but conceptually, it's right here. A big takeaway from this problem is that if you went to the Wronskian, it would be inconclusive, which doesn't mean they're dependent, but that might be a good thing to look for at that point, because it's a lot easier after that fact to prove dependence than independence.